Good afternoon, everyone, and welcome to our presentation, Connecting the Gut Microbiome to Human Health. My name is Aaron Troutman, and I'm a PhD student. I work under the direction of Dr. Corey Brower, and I had the privilege of having two awesome interns with me this summer, Aswani and Chris. To start, I'd like to ask a question. What do we do with the data that we generate in our labs? Well, generally, we publish papers. Those papers end up in journals, and sometimes it ends up in a book. For some of this research, it can be cataloged into a large database. We call ours the P2EP knowledge base. Super creative, I know. But this data can be further used to drive the scientific process. We connect databases in areas like plant nutrition, chemical compound information, and human health and disease. Many exist in this area, and even more. Due to the work of those who came before me in creating the knowledge base, we have a nice connection between the databases previously mentioned, connecting areas in plants, chemicals, genes, and diseases. However, a largely underrepresented portion of data lies within a hidden community inside each one of us. I'm talking, of course, about the microbiome. The microbiome can be found in unexpected places like the skin, the hair, the gut, the lungs, and the esophagus. This picture is a fairly accurate representation of the microbiome research, and the large unsorted pile is only ever growing. But all research had to start somewhere. The year was 1962, and a bulletin was published about a community of microorganisms living on tissue. As far as I can tell, this was the first published scientific acknowledgement of the microbiome. However, Louis Pasteur, commonly considered the father of microbiology, thought that life without microbes would be impossible, and that microorganisms are necessary for sustaining the life of an animal. Practical treatments predate this knowledge, however. In ancient China, patients were given a yellow soup to treat digestive issues. I'll let you guess what was in this yellow soup, but I can tell you it rhymes with goop. In more common times, we use a procedure called a fecal microbiota transplant to replace a microbiome of an individual suffering from a Clostridium difficile infection with that of a healthy one. As we had discovered bacteria in previously thought sterile environments, research has increased to a point where a method of organizing and databasing is necessary. This graph shows the increase from 2000 to 2017 in published microbiome research, and for the past 2 years, microbiome papers have numbered over 20,000. Currently, microbiome abnormalities have been implicated as factors affecting moods and mental health and a potential link to autism, the immune system, autoimmune disorders and allergies, and obesity and several cancers. Microbiome abnormalities have been linked to these diseases, and they affect Americans, people all over the world, and cost time, money, and in many cases, human lives. The thing is, we all need food, and we know that we get our nutrition from the things that we eat. However, so do the bacteria that live within our gut, which begs the question, what are the bacteria in our bodies doing with it? This brings us to our summer research. We're going to answer questions. First question being, how does the microbiome affect the plants that we eat, and how do the plants that we eat affect our gut microbiome? Fortunately, I only had 2 questions because I only had 2 interns. So I'll now turn it over to them to let them tell you about our work this summer.
Thank you, Aaron. My research question was based on how the gut microbiome affect the food we eat. So the food contains chemicals which are converted by this gut microbiome into metabolites, which are either directly absorbed by the body or either further metabolized by other gut bacteria. So this gut bacterial metabolism depends on various factors like the type of food we eat, the person's gender, age, and geographic region, but most importantly, the individual's gut microbial composition. So I was primarily focused on the polyphenol constituent of food, and most of these polyphenols are made biologically active by intestinal transformation, either by digestive enzymes or by the gut bacterial metabolism. So in the figure I have an example of the soybean polyphenol digoxin. And so we use lingomatics to text mine through millions of scientific literature and get this curated list of microbiome data in relation to polyphenol conversion and incorporate this into the database. So from this list, I have the proportion of major polyphenol converting bacterial genera, which includes Eubacterium, Bifidobacterium, Lactobacillus, Egertella, to name a top few. As an example illustration, I have the soybean polyphenol dietsin, which gets converted by gut microbiome into equol, which is found to regulate around 57 genes and is found to influence diseases like heart diseases, inflammation, various types of cancer. So I have, in the pie chart represents the proportion of bacterial genera that's found to be responsible for the production of equol. And it includes Slackia, Egertella, Lactobacillus, to name top 3. So the soybean polyphenol dietsin, which I mentioned earlier, is found to have antioxidant as well as anti-cancer properties, and it's also found to have inhibitory effect on tyrosine-specific protein kinases and topoisomerases, which are found to influence cell proliferation. And the metabolite equol is found to be more biologically active than the parent dietsin, and it's found to be influencing in the prevention of diseases like breast cancer, prostate cancer, heart diseases, and osteoporosis. So this picture is from a study done by the University of Pittsburgh on the health benefits of equol, and it represents that around 60% of Japanese population was found to be equol producers, whereas only 25% of the American population was found to do the same. So this shows the variations in gut bacterial metabolism and leads us to the question Chris is interested in.
Thank you. So equol production isn't the only functional difference we see in the Japanese gut. We also see increased acetate production and decreased methane production. So if you look at the heat map on the right, each row is a different grouping of genes related to a different functional group on the left. So for acetate production, we have 15 of these different groups, and for 13 of these in the Japanese population, we see that they have significantly increased expression. And for methane production, we see in 24 of these groups, they have significantly reduced expression out of 25 total. And the reason for this is the bacteria in the gut. Blaussia is a genera of bacteria that's commonly associated with acetate production. We can see here that the Japanese population has a higher abundance of Blaussia in the gut. And within Microbiome History is a species of bacteria associated with methane production. So we can see here that on the right, they have a much lower abundance of this species. So what kind of causes this is diet. So I picked a chemical that's found in a lot of different foods called Piceatannol to show you guys today. It's found in soybeans, grapes, cocoa, and Japanese knotweed. It's an invasive species a lot like kudzu, and if you're curious, tastes like extra sour rhubarb. Now, if we look at how Piceatannol affects the body when it's naturally absorbed, it affects 82 different genes, which are involved in various pathways relating to cancers, heart disease, and inflammation. If we look at how it affects the gut microbiome, it increases the abundance of Blaussia and Lactobacillus, which have been implicated in different pathways relating to inflammation, obesity, and digestive disorders. So to give you specific examples, Lactobacillus has been it's been shown to help alleviate diarrhea, but on the other hand, it's also been associated in higher abundances with obesity. So we kind of have to be careful about how we're looking at these things. To kind of sum up what I found over the summer, we see Bifidobacterium and Lactobacillus, two of the most commonly seen in my research, are two of the most common in probiotics. And that big 32% there is other. That's like a wide variety of different things that were found in five hits or less. So there's a very wide range of different genera per seed. And to kind of sum up, we see the gut microbiome can alter the chemicals that we eat, like we saw with diazine and meatball, and we see that the chemicals that we eat can change the bacterial abundance in our gut. So for future work, we're kind of putting puzzle pieces together from other people's research. So stuff like this would need to be verified through wet lab research from start to end. And then we also need to automate this process because right now we're doing everything manually. So there are always new findings coming out, and we would never be able to keep up if we had to do this on our own. We'd like to take a moment to acknowledge several key people who have been instrumental in allowing us to do what we do. And thank you all for your time. If you have any questions, we'll be available after the talk.
I believe we're going to take a short. Yes.
Finally, a question. This might be kind of barking up the wrong tree, so to speak, in this audience, but curious. The major consumer of soybeans are actually not humans these days, right?
Potentially.
It's fed to animals primarily, I think. Do you think this has any application in animal guts that we would want to look at that might improve their productions, so to speak?
It would definitely have implications in their guts. One of the interesting things is that we see differences in how different animals produce or react with foods, and different animals have different gut bacteria compositions, right? So one of the typical models is a mouse model, which is used to kind of compare to humans, and it's typically because humans object to being dissected and their colons taken out, but rats are a little bit more easier to convince to do that. But the differences are there, and we see differences in how the rat microbiome behaves and how the human microbiome behaves. So if we're testing food and we're saying, okay, I'm going to feed the cows a ton of soy, or I'm going to feed chickens maybe a ton of soy, whatever animals you're feeding, a lot of this foods, you may be able to then produce healthier chickens or healthier cows based on their gut microbiome compositions, or so I think it's definitely an avenue of research that is worthy to explore. Thank you. I believe we're going to take a short break really quick, probably about